All right. So next up, we have Mostafa, who's in the College of Engineering in the Department of Mining Engineering.
Thank
So
you.
take it away, Mostafa.
Hi, everyone. Thank you very much for this opportunity. I'm going to talk about one of the main challenges that exist in industrial processes, and that is the generation of wastewaters and the technology that we have developed to effectively remove heavy metals and toxic species and simultaneously recover through solar energy. Okay. Uh, we all know about how critical the water is, but the water is not only a resource; it is actually a lifeline, and it sustains ecosystems, ensures human well-being, and drives industrial development around the world. Industrial development and expansion of urban areas have significantly increased the water consumption as well as the consumption of other natural resources. Among various industries, mining is heavily relied on water consumption for a variety of operations, making water a fundamental component in the supply chain of the materials that we are dependent on for our everyday life. The demands for minerals are continuously increasing as the world is transitioning to a clean energy economy. And as a result, water-related challenges are intensifying due to increasing mineral production rates. In addition to water shortage problems, mining activities produce a large amount of wastewaters, introducing significant fluxes of heavy metals and toxic species, which can pose severe problems to the surrounding environment. A part of this wastewater is recycled as a processed water, but a major part of that is just discarded in disposal basins called evaporation ponds. Uh, Evaporation ponds may be a cost-effective strategy for wastewater management, but it ignores the benefits of water recycling, and also it can pose severe impacts due to leaving large concentration of heavy metals and toxic species as the water evaporates. So it is essential to have novel and efficient technologies to treat water disposed in evaporation ponds, since the conventional technologies are not applicable to uh, these kind of evaporation ponds and wastewaters due to economical constraints. There are various technologies for water and wastewater treatment. Among various technologies, sorption-based technologies are uh, reliable options for water treatment due to their sustainability, reusability, and higher efficiency in comparison with other technologies. In this work, we have proposed and developed three-dimensional aerogels made of natural polymers and having photothermal properties to not only remove heavy metals, but also uh, recover water through enhanced solar evaporation mechanism. Aerogels are actually regarded as a promising platforms because of easy operation, relatively low cost, high reusability, and as a low density and high porosity and high efficiency compared to other forms of biopolymers like powders and flakes. To prepare the aerogels, we use chitosan as a natural polymer with abundant functional groups capable of binding with metal ions. Interesting properties of chitosan, such as being biocompatible and biodegradable, and flexibility for structural customization makes this proposed technology more sustainable. Also, photothermal properties were incorporated into the surface of aerogels using carbon nanotubes and polydopamine as a muscle-inspired polymer to simultaneously detoxify wastewaters and remove heavy metals from there. Okay. All aerogels were fabricated using freeze-drying technique and an eco-friendly process. To functionalize the aerogels, carbon nanotubes were first carboxylated to just provide more hydroxyl and carboxyls on the surface of carbon nanotubes to just increase the functionalization efficiency. Here you see the surface morphologies and structures of the aerogels studied by scanning electron microscopy. The chitosan aerogels displayed a smooth and closely contacted lamellar network with surface area around 2.7 square meter per gram. And incorporation of carbon nanotubes disrupted the laminar morphology of the chitosan aerogel, resulting in the formation of wrinkles and small pores on the sheet-like structures. The incorporation of polydopamine into the aerogel resulted in higher porosity with a cellular structure and cell dimensions ranging from 5 to 50 micrometers. And also the incorporation of polydopamine nearly doubled the surface area to around 4.7 square meter per gram due to the formation of a uniform cellular structure and preventing the agglomeration of carbon nanotubes. All aerogels showed great water absorption capacities. However, functionalized aerogels demonstrated higher water absorption capacities due to the presence of more available OH and NH groups, reaching the capacities around 8,000% after being immersed in water for 30 minutes. Regarding photothermal properties of aerogels, the chitosan aerogel showed just limited light absorption, reflecting almost 95% of light in the infrared region, while functional aerogels displayed strong light absorption properties, absorbing more than 95% of light in a broad range of spectra, including infrared, visible, and ultraviolet regions. Here you see the infrared camera images of the aerogel surfaces exposed to light in the near infrared range with wavelength around 760 nanometers. The surface temperature of the chitosan did not change significantly after 15 minutes being exposed to the light condition, while the surface temperature of functionalized aerogels increased to around 100 to 130 degrees centigrade after 5 minutes of being exposed to light condition, indicating the rapid photothermal conversion of aerogels after modification with polydopamine and carbon nanotubes. In this slide, you see the absorption capacity of aerogels towards arsenic as a toxic species commonly found in mining wastewater. The absorption rates of the aerogels were initially very high in the first 15 minutes, and then slowly increased to their equilibrium value after 30 to 90 minutes for all aerogels. The fitting of kinetic data to the intraparticle diffusion model suggested three distinct absorption stages. In the first stage, chitosan aerogel showed faster absorption, probably due to its looser structure in water. In the second stage, the functional aerogels reached higher amount of absorption, demonstrating more pronounced diffusion controlled absorption process. Also, the results indicated that the absorption capacity of all aerogels was higher in acidic environment, which is so good because most of the mining wastewaters are mildly acidic. And aerogels can be easily regenerated just by immersing in 0.1 molar sodium hydroxide solution. And after regeneration, we just reuse it for 5 cycles. And as you see, the absorption capacity remained as high as 90 to 95% after 5 cycles of absorption and desorption. But in the case of chitosan aerogel, the efficiency just dropped to around 80% because of its lower mechanical properties and stability. In summary, these kind of platforms work for evaporation ponds. They can just float by itself on the surface and just absorb. Evaporation ponds are not only used for wastewater management in mining industry, they are used for several industries like oil sand treatment, food industry, and we can regulate the hydrophilic properties of aerogels and polysaccharide materials to just control the evaporation rate depending on the weather condition and also geographic condition that we are going to work in. Thank you so much.